All right, so let's look at another thermal property of glass, and that is the viscosity. So let's start with a question. So, um, so based on other classes you've taken, maybe you've studied this a little bit. So I just kind of want to see where everybody's at. So if you can go to the quiz, pause the video and go to the quiz and answer these questions to kind of see where everybody's at. But what I'm gonna ask for is, uh, your definition. What do you think viscosity is? And then tie that to what we're studying with inorganic glasses. So why do you think it's important for this field? So answer those two questions in the quiz, and then come back and we will discuss. All right, so let's go ahead and go through these real quick. And I'm going to start with the first, or I'm going to actually start with the second question, and that is, why is this important to us? So viscosity is really important to the processing of glass. So I put a couple pictures up here of actual glass processing. So these are the furnaces where glass is made, and then these are injection molding apparatus for making bottles. And so viscosity is important for all of this. So it's important for the melting conditions. So starting with the raw ore, how do we melt that? And then basically make that into a formable material. It also matters for the time and temperature to homogenize. So basically getting everything the same. It's going to matter for what we call a critical cooling rate. So the sort of separating between a crystalline material and a amorphous. So how quickly do we have to cool to get that amorphous material, right? So if you have to cool extremely rapidly, then that's not a practical material to make in real life. And the last part is actually annealing stresses. So the process of making glass will inevitably put stress on it. And so we often have to do some type of annealing, excuse me. And that annealing is going to be tied to the viscosity of the glass. So these are all kind of important areas. So viscosity is basically one of the important properties when it comes to processing. All right, so now let's answer the question of what viscosity is. And so let's look at it from sort of a mechanics point of view. And so viscosity, in a simple sort of definition, is the ratio of the applied shear stress to the rate of flow. So we apply a shear stress. And so this is kind of, if you remember shear, this is an example of a shear on a fluid, right? We have two plates, one on bottom, one on top, and we apply a force going to the right in this case on the top plate, and then there would be a force to the left from the bottom plate, and that's that shearing motion. And so here it's called F. And then we're looking at the rate of the flow. So how quickly does it move upon that applied force? So here we have the shear force, F. We can translate that into an applied shear stress based on the area that we have. So A is the area of those plates. And then we also have what else? We have the strain rate. So this is the rate of flow, as we're looking at how quickly it strains. So that will be our epsilon dot. So when you see the dot typically refers to rate. So strain and then rate. So it's just going to be seconds inverse. And then the flow is the sort of script V that we see, and then the area, you saw that. And we typically use the symbol here, nu, for viscosity. Although again, you're likely to see, if you look at different resources, different symbols for this. But in this case, this is viscosity. So very simply, we apply a shear stress, and then we look at the flow. And so we can look at applied shear stress over strain rate. All right, so for glasses, viscosity is tied to those bonds that we saw. So everything is kind of coming back to the silicate structure, right? So when we saw the SiO-Si bond, right, that was a bridged oxygen. And we break those bonds when we add those modifiers. So in this plot, we're looking at the increase of sodium, which is a modifier, into the glass. And we see that increasing that breaks up these bonds, and therefore it makes it easier to flow, right? The part down here, it makes it easier to flow when that happens. So it lowers viscosity. And so this is viscosity, so log of viscosity, and then as a function of temperature. Viscosity always changes with temperature, but the main thing we see here is that once we increase the soda content or sodium, we're going down, and that going down means a lowering of the viscosity, right? So that means it's going to be flow more and more like a liquid, faster response when we modify it and break those bonds. And we can model this type of log temperature relationship with this VFT equation that you see here. So that's a very common way of seeing the viscosity. All right, so this is a pretty typical plot of showing viscosity as a function of temperature, particularly for glass. So again, we have log viscosity. So when you see a change of 1, right, that's a very large change because it's a log scale. So keep that in mind. And then temperature here as well. So this is a typical curve, what a typical curve would look like for viscosity of a glass. And we kind of have it broken down into multiple regions. So again, I like to start at the highest temperatures. So if we go down here to the highest temperatures, you see in this regime, this is where it's melting or casting, right? So this is where it's melted. This is where we can, it easily flows and we can process it at that point. So the highest temperatures are where that's happening. Then the first kind of critical point we see here is at when the log of the viscosity is 5. This is known as the working point. And this is basically, again, it's defined by the viscosity, but it's because of that, it means that this can be readily shaped, formed, or sealed. So this is where, a lot of the flowing and shaping of bottles and things like that during the processing of glass would happen, right? We want to be able to work it, right? So that's the name, where the name comes from. So the working point. So if we continually decrease the temperature, the viscosity is going down. The viscosity is going up. The viscosity is going up, making it harder and harder to flow, right? And so the next point is defined again at a certain point is the softening point, and this is where it's defined as it elongates at 3% per second. And so this is another sort of critical area that glass makers need to know because that will that temperature at that viscosity will tell us when we have this certain elongation. All right, and if we continually decrease the temperature, we see that the next, and it's actually a steep rise at this point, the next point is known as the annealing point. And at this point, the glass isn't moving as freely as it was definitely at the working or softening point. So it's more or less, you can see it's in the area of the glass transition temperature. So it's not freely moving as quickly as it was up here. So these aren't useful for processing in terms of making the shapes. It's more for reducing the strain. And so for the annealing point, this is defined the viscosity at which the internal strain can be reduced in 15 minutes. So that's pretty quick, right? We reduce any strain that's in the material in 15 minutes. And again, it's right in the range of the glass transition, so you can still have some shape change over time. And then if we go even higher, lower in temperature but higher in viscosity, we get to the strain point, and this is where you can reduce the internal strain in 4 hours. So you can see just this sort of couple orders of magnitude here, and that changes from 15 minutes to 4 hours. So that's because we're very close to the glass transition temperature, and those properties can change drastically. So if we're at or near the glass transition, we can still have motion, but it's at a much smaller scale where it's relieving the internal strain. But over time, you could have shape change as well. All right, so let's look at how we measure this viscosity, just like how we measured the thermal point of glass transition. So there's multiple methods for viscosity. One of the measures is viscometer, so very aptly named. And then we also have a fiber elongation method. So the main difference in these methods is the types of materials or the state of material that you can use. So the viscometer is really good for the more fluid type or liquid type materials, and so it's only good for about up to 10 to the 7 Pascal second, which is the unit of viscosity. So it's on the lower side of viscosity. So if you have something more like a liquid, viscometer will do the job. And basically how this works is that we have a cylinder, something like a stainless steel or something like that, that's inside the material, and we rotate it. And that gives us that shear stress, and we look at the resistance to the material. So we kind of measure the strain on the instrument as we rotate the cylinder. And so that's how we get this sort of shear that we saw in the previous slides. So instead of doing this type of arrangement, we do it as a cylinder rotating, but it's the same geometry. And so it's governed by this equation. You don't have to know this, but this is just kind of giving you what the viscosity, how that's calculated. The other method, the fiber elongation, is basically what it sounds like. You have a fiber of your material, so it's more in that solid state, and then you basically hang a given weight on it so that you have gravitational force wanting to pull the fiber down. So we know the length and we know the radius, and we have a given force on that fiber. And so this is definitely good for the higher viscosities where it's more solid-like, and we measure that extension rate. How long does it, how fast does it strain under this condition? And so that's basically the equivalence of what you're seeing here. So the softening point, it elongates at 3% per second, right? So that's how we measure it with something. We would measure it with something like this, a fiber elongation. So these are kind of the two methods that we can talk about in terms of measuring viscosity, and they're really defined by what the viscosity is. So you may have to switch from one to the other based on the material. And even in viscometers, there's different adapters and different cylinders that you can use based on the viscosity of the fluid.